Dear students, in last class we have studied the transfer function of Iir system in Z domain, that is h of z equal to b0 plus b1 z raised to minus 1 plus b2 z raised to minus 2 plus and so on up to bm into z raised to minus m by 1 plus a1 z raised to minus 1 plus a2 z raised to minus 2 plus and so on up to an z raised to minus n. Also we studied the difference equation of Iir system as y of n equal to minus a1 y of n minus 1 minus a2 y of n minus 2 plus minus an y of n minus capital N plus b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus and so on up to bm x of n minus m. And also we have studied transfer function of Iir system in Z domain and discrete time domain. In Z domain, h of z is given by b0 plus b1 z raised to minus 1 plus b2 z raised to minus 2 plus and so on up to b n minus 1 into z raised to minus of n minus 1. And in discrete time domain, y of n is equal to b0 into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 plus and so on up to b capital N minus 1 into x of small n minus capital N minus 1 bracket complete. These Iir systems and Fiir systems may be represented with the help of block diagrams. And representation of these h of z and y of n by means of block diagrams is called as realization of a digital system. For realization of this Fiir and Iir system by means of h of z or y of n, we make use of various mathematical operations like multiplication, addition, delay, and for all these operations different shaped blocks are used. And to implement such an equation, those blocks will be connected in one particular order. So now we will take up the basic blocks which are used to construct the block diagram for Fiir system and Iir system realization. So now write here basic elements of block diagram. Elements of block diagram. time domain representation, Z domain, adder, x1 of n and x2 of n may be added by using adder block. Inside this block we write plus, and output of this box will be x1 of n plus x2 of n. In Z domain, x1 of z plus x2 of z is equal to x1 of z plus x2 of z. Constant multiplier. Say I have to multiply signal x of n by a, then I will have to pass x of n through the constant multiplier box to get a into x of n. Similarly, in Z domain, we have to pass x of z through constant multiplier to get a into x of z. Next element is unit delay element. To have any input signal delayed by 1 unit, we have to pass through the delay element box in which z raised to minus 1 is written. If input is x of n to this delay element box, then we get at the output x of n minus 1. If I have to get x of n minus 2, this output I have to pass through one more z raised to minus 1 box. That means I have to pass it 2 times through z raised to minus 1 box. Similarly, in case of Z domain, we get output x of z into z raised to minus 1 when x of z is given as input to delay element box. as we delayed input signal here by 1 unit, we can advance the input signal by 1 unit also, that is by means of using unit advance element. But here inside the box we write z raised to 1. Z raised to 1 is z only, so we will simply show here z. If input is x of n to this advanced element box, then output will be equal to x of n plus 1. Similarly, if input is x of z in z domain to the advanced element box, then output will be z into x of z. We can have different types of structures for realizing the Iir systems. Those structures are direct form 1 structure, direct form 2 structure, cascade form structure, and parallel form structure. Now you can note down these different types of structures used for realizing the Iir systems. And we will learn realization of Iir systems using different types of structures by means of examples directly. Now we will see how to realize the Iir systems using these various types of structures one by one. We will take first one. Direct form 1 structure of Iir system. Consider the difference equation. Governing an Iir system. That is y of n equal to minus sigma m equal to 1 to capital N am into y of n minus m plus sigma m equal to 0 to capital M Bm x of n minus m. Y of n is equal to minus a1 into y of n minus 1 minus a2 y of n minus 2 plus and so on up to minus an y of n minus capital N plus b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus and so on up to bm x of n minus m plus b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus and so on up to bm x of n minus m. On taking z transform of this equation, we get on taking z transform of y of n y of z equal to minus a1 z raised to minus 1 y of z minus a2 z raised to minus 2 y of z plus and so on up to minus an z raised to minus n into y of z plus b naught into x of z plus b1 into z raised to minus 1 x of z plus b2 into z raised to minus 2 into x of z plus and so on up to bm into z raised to minus m into x of z into x of z. Now this equation for y of z can be directly represented by a block diagram. How to do that we'll see on next page. For reference purpose, I have written the equation written on last line in last page once again here. Now the system output here is y of z and the inputs are x of z, delayed x of z and delayed y of z also. So we'll take x of z first as input. X of z is multiplied with b naught. So we'll make use of multiplier box and in that we will write b naught. So what we'll be having output as now? We'll be having output as b naught into x of z. So we got this term here now. B naught into x of z is here, so I got that term here. Next, we have to add b naught x of z with b1 into z raised to minus 1 into x of z. Z raised to minus 1 is used for delaying x of n by one sample, right? So I will show here z raised to minus 1. That means at this point I am having now z raised to minus 1 into x of z. This we will give as input to the multiplier box, and in that box we'll write b1. So here we are now having b1 z raised to minus 1 x of z. So this term we obtained. Next we have to get b2 z raised to minus 2 x of z. Already here I am having z raised to minus 1 x of z. So here simply I will include one z raised to minus 1 box or one delay box, z raised to minus 1. That means z raised to minus 1 into x of z into z raised to minus 1. That will be z raised to minus 2 into x of z. That means 2 sample delay will be there. So here output is z raised to minus 2 into x of z. Now this output of this delay box is to be multiplied by b2. So one more gain or multiplier box. So here b2. Output will be b2 into z raised to minus 2 into x of z. Next we are having here so on up to dash 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 dash. Z raised to minus 1. Dash 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 z raised to minus 1. Output of this box here is equal to z raised to minus m into x of z. Gain is bm, or constant to be multiplied with this term here is bm. So we get output as bm into z raised to minus m into x of z. Next we have to add all the outputs here. So for addition we will make use of adder. So I will show one adder here. For adding the two outputs b2 z raised to minus 2 into x of z and bm z raised to minus m x of z, we will make use of an adder. Here I have shown dotted line because here we have skipped off some of the terms. So similarly here also we have to skip off some of the terms. Now this sum that I am going to get here, I will add with b1 z raised to minus 1 x of z. Finally, the output of this adder I will give to the summer, to which another input is b naught x of z. That means I have added these various outputs and my output will be now here. If we look at y of z equation here, these all the x of z terms here are added to the y of z terms. So now I am having the sum of all the x of z terms and their delayed versions. Here, let us say output y of z is available to us. Now, to get the first term, I have to delay y of z by 1 unit. So I will make use of one delay box here, that is z raised to minus 1. So here I get y of z into z raised to minus 1, and this should be multiplied with minus a1. So I will show multiplier with constant of minus a2. The output of this multiplier will be now minus a2 into z raised to minus 2 into y of z, and on this side we will show dash 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 z raised to minus 1. Output of this delay box is y of z into z raised to minus n. Let us show here one multiplier box, and inside this we have to write minus an. Output of this box will be minus an into z raised to minus n into y of z. Now we have to add all these outputs. For that we will make use of adders. To add x of z and their delayed versions to the delayed versions of y of z, we will join these two. When x of z and its delayed versions and delayed versions of y of z are added, we get output y of z. So this is how we can realize an Iir system using various basic elements, and this type of realization is called as direct form 1 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . structure of Iir system. In this structure we are having m plus n plus 1 multiplications, m plus n additions and m plus n delays. This point we will note here. In this structure, m plus n plus 1 number of multiplications m plus n additions and m plus n delays are present. It means that m plus n memory locations, in bracket you write, equal to delay units are required. The order of Iir system is the highest value of capital N. If number of delays is equal to the order of the system, then the structure is called canonic structure. But here m plus n is not equal to n. Therefore, direct form 1 structure is non-canonic structure.